Hi, it's late August of 2020 right now. The fall semester here at Bethel is about to start. I'm at lecture 11 in this series. My students are coming on campus and we'll start watching lecture 1 soon, in about a week or so, and we'll be meeting in class to work through problems together. Hopefully I'll be able to stay ahead for the entire semester and hopefully we can stay on campus. A couple lectures ago, lecture 8 or 9 or so, I mentioned it seemed like the linear algebra and differential equation content of the course were pretty far apart. Starting here in lecture 11, if you watch both parts, there is going to be a connection between the two subjects, kind of a deep connection that is important to realize. And the topics in differential equations and linear algebra will continue getting closer and closer together here as these lectures move on. But again, there's a connection in 11A and 11B that I'm going to point out as we go. Lecture 11A, we're going to use technology to do a harder bifurcation example. Lecture 10A was about a lot of bifurcations that we could think about by hand, but you really need technology for this one. We'll also talk about a new topic, first order linear, emphasis on the word linear. Hey, that's a relationship to linear algebra. Ordinary differential equations and the method of undetermined coefficients, which sounds like a fancy method, but it's really nothing more than educated guessing. Lecture 11B, linear algebra, is about linear transformation from a higher dimensional space to a lower dimensional space. In 10B, we did lower dimension to higher dimension. Talk again about kernel and image. Then we'll also talk about composite linear transformations, where you compose those functions and how that's related to matrix multiplication. Very first thing to do, though, here in lecture A is I think it would be good to review that linearization theorem that we used in lecture 10A, also called the Hartman-Grobman theorem, though in one dimension. The general Hartman-Grobman theorem, which we really use later in the semester, applies to higher dimensions. It's simpler in one dimension. Suppose y0 is an equilibrium point. Again, I emphasized last time, whoops, wrong way there. It's very important to realize you're assuming that y0 is an equilibrium point. If it's not an equilibrium point, don't use this theorem. It doesn't apply. For an autonomous ordinary differential equation of this form, dy dt equals f of y, that's a first order equation because it only involves the first derivative. It's autonomous because the right-hand side is independent of t. It only depends on the dependent variable y. F is assumed to be what's called continuously differentiable, which means not only that f prime exists, but f prime is also a continuous function. And I showed you in lecture 10A that there are some wild examples that are not continuously differentiable. In fact, there was even one example that was differentiable. The derivative always existed, but the derivative was not continuous everywhere, and that was kind of a problem. You cannot apply this theorem in that kind of situation. On some open interval containing the equilibrium point y0. Two main bullet points, and then a third bullet point kind of just completes this thing. These first two are ones you can actually prove, though. If f prime of y0 is negative, then y0 is a sink, when f prime of y0 is negative. And if f prime of y0 is positive, then y0 is a source. Okay, and I gave you visual reasons for why this is true in lecture 10A. If you need to be reminded of that, you should watch lecture 10A, perhaps about 8 or 9 minutes in, I forget exactly. Let me just say here that this will generalize to higher dimensions and becomes even more significant in higher dimensions, okay? We're going to linearize near equilibrium points when we talk, for example, about phase planes and phase spaces. And the derivative in that situation is still relevant, though it's a higher dimensional derivative. It's called a Jacobian matrix, if you've ever heard of that. The third bullet point isn't really a fact to prove, it just sort of completes what you can say. If f prime of y0 is equal to 0, then pretty much anything can happen. And again, I drew graphs in lecture 10A to illustrate that anything can happen. It could be a sink, a source, or a node. Okay? So you need more information. You essentially need the graph of f to decide. All right, let's go on to our challenging bifurcation example. We're going to once again consider a one-parameter family of autonomous first-order ordinary differential equations. Mu will be our parameter. For my students in the book, oftentimes the letter A or alpha is used as a parameter, but I like using mu. In the examples from lecture 10A, mu was always added at the very end, and it really represented a vertical translation. In this example, not only is the degree going to be higher, it's going to be a fifth degree, but I'm going to put mu in there in a couple spots. right here and here. And it's not just adding mu, so it's not just a simple vertical translation. It's being multiplied times y to the fourth and negative 2y. It's coming in some sort of real complicated way. It should be very unclear what in the world would be going on with this family of differential equations. But again, the point of bifurcation theory and making bifurcation diagrams is we want to understand what goes on for the phase lines for this system, for this equation, as mu changes. Now, mu is a constant initially. You think of this equation as defining a differential equation for a constant value mu, but then you change your perspective and say, hey, what happens as mu changes? Okay? And the bifurcation diagram, in a sense, is kind of like a movie of what happens as mu changes, and the Mathematica code will illustrate that. We're going to use technology to try to draw the bifurcation diagram and estimate the bifurcation values of mu for this particular one-parameter family. I will show you the Mathematica here in a minute. But here is a screenshot of the relevant Mathematica animation that we get to at the end. And I picked mu to be 2.6. Okay, I could have picked something else. I picked it to be 2.6. Here's the picture. This picture, first of all, you can see that mu equals 2.6 right there. Shows you two graphs. It shows you on the left the graph of the right-hand side function when mu is 2.6. Kind of looks like a cubic, but it is a fifth degree. The fact that it's kind of strange looking in here, you don't see this kind of thing where it's sort of, it's concave down and concave up, and sort of almost, it's almost like the second derivative has maybe a double root or something right around in here. That kind of thing doesn't happen with cubics. It's kind of weird looking. I'm not proving anything and saying that. Makes you believe that maybe this is a fifth degree, and it is, in fact, a fifth degree, though it only has 3 real roots. When mu equals 2.6, that's what that looks like. Now, you look at the intercepts of this, the y-intercepts where y is horizontal here, at about negative 2.6 or something, positive, 0.2 and maybe 0.8 or so. Those become equilibrium points for the phase line over here. This is the bifurcation diagram here, and this is one particular phase line at mu equals 2.6. Mu is horizontal, y is vertical in this case. This blue line is supposed to be the phase line, though it's not complete because I haven't drawn the arrows yet. I purposely left off the arrows because we should think about them. We've got 3 equilibrium points. Are they sinks, sources, or nodes? You can use the linearization theorem. This equilibrium point at around y equals negative 2.6 or 7 or 8 or so has a derivative, a slope of the tangent line that's positive. The linearization theorem says then that this point at y equals negative 2.6 or negative 2.7 or so is a source. I should draw arrows going away from it. And that should make sense if you think about the sign of f as y increases through this point. It's negative to the left of it and positive just to the right. Solution curves for the differential equation have negative slopes when you are below this point. In the slope field, you'd be below that equilibrium solution, that horizontal line solution. They decrease. You got to put a downward pointing arrow. And in between here and here, which is in between here and here, the function's positive. dy dt is positive. Solutions have positive slopes. They are increasing. So you put an upward pointing arrow. This equilibrium point right here has a negative slope. The linearization theorem is going to say that this point right there is a sink. So put a downward pointing arrow in there. Yeah, and that makes sense right here. F of y is negative right there. Therefore, dy dt is negative. Slopes of solutions are negative. They are decreasing. This is a downward pointing arrow, even though it's kind of hard to see there. And this point is a sink. Finally, this point right there has a positive slope. The linearization theorem would say that this point right here is a source. We already know we've got downward pointing arrows right there. When y is above that point, this function's positive. You're going to have upward pointing arrows. The solution curves are increasing over there. What would happen at other values of mu? Evidently, a bifurcation is going to occur right about here. When mu is perhaps about 1.5 or so, And probably, based on trying to be consistent with the rest of the diagram, this point is going to be a node with arrows pointing upward here and upward there. It's like the downward pointing arrows in there kind of go away as mu decreases there. You're still going to get a downward pointing arrow here. This equilibrium point is going to be a source still, but this one's going to be a node. Evidently what happens here is mu decreases from about 2.6 to about 1.5 is this graph, as mu decreases, goes upward. And these points probably merge. You'd have a tangent, not only a y-intercept at this point right here, but also the red graph would be tangent to the y-axis there. When mu is less than that, but bigger than over here, when you're between here and here, to be consistent with these other arrows, going to be upward there, downward there. This point is going to be a source. This point's going to stay being a source over here as well, to be consistent. And continuing further, it'll stay being a source. But you have another bifurcation near mu is negative 3.4 or something. I'm just guessing there. That point's going to be a node, upward pointing arrow there. And then when mu is less than about negative 3.4, or whatever that happens to be, you've got 3 equilibrium points. And to be consistent with the other arrows, this one's going to be a source, this one's going to be a sink, and this one down there still, like we mentioned before, is a source. So we are understanding what happens for any value of mu. We're thinking about infinitely many phase lines all at once. And those phase lines tell you about the behavior of y for whatever this might happen to model. Now, an equation like that, it's hard to know what it might model. Okay? It's just an example without an application. But if it did model something, you could see how y changes as mu changes. If mu is very negative, what's the end behavior of y? Well, it depends on the initial conditions, but initial conditions in here would go to that value of y. Initial conditions up here would go to infinity. And initial conditions down there, if y could be negative in the application, go to minus infinity. The phase lines tell you what happens to y. Okay? Let's go to the Mathematica. And I don't want you to focus on the Mathematica code itself so much, although you will be able to see it here. But focus more on the big idea, what in the world is going on. So this is going to be an animation of the plot of f itself without the equilibrium points shown. And you can see how mu increases, how the graph changes. It's not a simple vertical translation because mu comes into the equation for f in a more complicated way. This code will give us the equilibrium points with the solve command, solving for y as functions of mu, and we can see for different mu's how those equilibrium points change. Sometimes they happen to be complex numbers. This is the imaginary unit I, which means focus on the ones that are not complex. Those are the real ones. Sometimes there's one real solution. Sometimes there's 3 real solutions, like here, there, there, and there. Those correspond to the black dots, the equilibrium points. And I could plot those as functions of mu. This one is doing a lot of computations, so it takes a little while. This is essentially the bifurcation diagram. I can make, put the dots in there for the graph of the right-hand side function and see how those intercept points, which are equilibrium points, change as mu changes. Mu is increasing in the animation, whereas when I was looking at the diagram, I was thinking about mu decreasing. And here I put it all together to make essentially the right-hand side function and the bifurcation diagram, showing you what happens as mu changes. Though I did not take the time to put the arrows in there. I probably could, but it would take a little while for me to figure out how to put the arrows in there on the right. Okay? But again, for example, if I recall correctly, if this value mu, which is close to 2.6 there, that one was a source, this one was a sink, and that one was a source. Okay, and it stays consistent. When do bifurcations occur? said one was close to mu equals 1 point, I forgot, 1.5 or so? What happens when mu is close to 1.5? Close to this value. Not exactly at the bifurcation value there, but the red graph is not only touching the y-axis. If these points were merged into just one point, you'd have a double root there. The derivative would also be 0 there. And if I was back at mu equals about negative 3.5 over here, real close to this value, not exactly. It's hard to get it exactly there. Well, we're close. Now here, near 2.4 or so, which matches the second coordinate here, right there, we're close to another bifurcation. Notice the graph is very close to intercepting it and being tangent at the same time. Not only f of y being 0, but f prime of y being 0. So in general, in our quadratic examples, we could use the quadratic formula to help us find bifurcation values. But in general, what you have to do is you have to solve a system of equations. Where does f of y equal 0? And where does f prime of y equal 0? Solve for both y and mu. These are going to be nonlinear equations. In general, that might be very difficult to solve, especially by hand. And sometimes you might have complex number roots. But it looks like these first two possibilities are real answers. And notice mu is close to negative 3.5 there and close to positive 1.5 there. Okay? And in fact, if we want to get real close to one of them, we could, even in this animation, we could just go ahead and plug in one of them. 1.4985 was one of them. 1.4985 is very close to one bifurcation value. And you can see essentially we're at one dot there and one dot there. Not exactly, but these are good approximations. Okay. So I hope that's really interesting to me that we can do all this. This is one of the most interesting parts of the course to me. And when we go to higher dimensions, it gets even more interesting. Even wilder things can happen. Okay? And we'll have bifurcation diagrams that are really three-dimensional pictures. It gets pretty wild. All right. On to our second main topic, and that was linear equations. And I want to set this up by thinking about an application. There's a lot to show you here. For the sake of time, I want to go pretty fast. Okay? So you may want to just focus on what you see here and what I say. Don't necessarily take notes, but go and look at the PowerPoint. My students, I'll make it available for you on Moodle. For anybody else watching, I'll make it available on the Google Drive. I'm going to go pretty fast here, but pay attention. So we're going to first talk about an application, modeling financial growth and flows. A person initially places $2,000 in a savings account that pays interest at a rate of 0.5% per year, compounded continuously, like, every moment of every day. Now that doesn't really happen with bank accounts. Usually bank accounts, they give you money quarterly. But for the sake of using differential equations to model the growth here, it's simplest to assume continuous compounding. In real life, financial flows of money are happening literally every second of every day around the globe. And you can think about investments growing literally every second of every day. And in those situations, it's definitely better to model them with differential equations. Not so much with bank accounts, but humor me here, okay? Don't worry about it. Savings accounts pay tiny interest rates. Usually it's even lower than that these days, here in 2020. Back when I was a kid in the 1980s, we had really large savings account interest rates. I kid you not, 8%. Of course, inflation was really bad then too, really high. So you had to get high interest rates in your savings account, otherwise you wouldn't put the money in it. Suppose a person arranges for not only to have that $2,000 deposit first, but also to have $10 per day being deposited automatically into the savings account. Okay? Now that's not depositing money every second of every day, it's just once a day. But that's often enough over the course of the year that we can effectively model this with continuous deposits. Write a differential equation for A of t, the amount on deposit after t years. Assume that daily deposits is close enough to continuous deposits so that we can use a differential equation in our model. And the final goal is to find the amount on deposit after 10 years. Okay, so again, I've got to go quickly here. Here's the basic principle. The rate of change of the amount of money with respect to time in dollars per year, it's good to think about units here, is a sum. There's the rate of growth that comes from interest, earned not only in the $2,000, that's the initial deposit, but also the money that keeps going in effectively every second of every day. That's what you're pretending, at least. That's one part of the growth, but also plus the rate of growth from the actual deposits themselves, without thinking about interest for those. What's the rate of growth from interest? It's 0.5% times the current amount as a rate. That's a relative rate of growth. And you have to convert it to a decimal, multiply that amount by 0.005. And then add this constant rate of growth as a rate of growth per year. You've got to convert it to being years. So this is what we get. 0.0005a, that's 0.5% of the given amount at any moment in time. That's got to be in the background of your mind at any moment in time. Plus 10 times 365.25 is the rate of growth from deposits in dollars per year. $10 per day times an average of 365.25 days per year to give you dollars per year, which is 3,652.5 on average over 10 years, thinking about leap years. This is an autonomous right-hand side. It's an f of a. So I could use separation of variables here. But, and this is the main point here, it also turns out that we can just make educated guesses for an equation like this. How? Well, start by realizing there's an equilibrium solution. What are equilibrium solutions? Remember, they are where, for an autonomous equation, where the right-hand side function always equals 0. Actually, you can find equilibrium solutions sometimes for even non-autonomous equations by setting the right-hand side equal to 0 and seeing if you can find horizontal lines where, in this case, a is constant. Usually it's y, where the right-hand side function is always 0. So I set f of a in this case equal to 0 and solve for a. And we'll get an equilibrium solution, if there are any. And there is one. We're looking for an equilibrium solution. A is a constant for all t. I'm putting the extra phi of t in there to emphasize this really is a function of t. You know, in our book by Blanchard, Devaney, and Hall, the Differential Equations book, they never put phis of t in there. They just call this a or a of t even. It's a constant function. I just want to emphasize that here. Set the right-hand side function equal to 0, solve for a. So we get 0.005a plus 3652.5 equals 0. Subtract 3652.5 from both sides and then divide both sides by 0.005. And you get negative 730,500. A negative amount? Yeah, it's okay. Now, of course, there's not going to be a negative amount in that account, but this is helpful in finding the solution that we are after. The equilibrium solution is not relevant in and of itself. However, it's going to help us find a general solution. Note that any solution of what's called the associated homogeneous ODE, where we get rid of the 3652.5. We're not thinking about adding $10 every day, but instead just thinking about that initial deposit in a sense. That's called an associated homogeneous ODE. And the reason it's called homogeneous is because when you subtract the 0.005a from both sides, you get a 0 on the right-hand side. That's the reason it's called homogeneous. This is going to be the part that's going to be related to linear algebra in lecture 11b. So if you watch that, pay attention here. Any solution of that would have the property that when added to this constant function, this equilibrium solution, we would get a solution of the original ODE, the original. That's got the 3652.5 there. That's non-homogeneous, because if I wrote it like this, it would have the 3652.5 over there. Why? This is the heart of linearity in the situation. If I called psi of t a solution of this homogeneous equation, and I added it to negative 730,500, and saw, is this a solution of the original equation, what would that mean? That would mean that when I take its derivative, I should get 0.005 times itself plus 3652.5. When you take the derivative of something like this, the derivative of a constant is 0 and the derivative operator is linear. This simplifies to psi prime of t. That's the left-hand side of the original equation. The right-hand side, plug it in there for a, would give you 0.005 times psi of t minus 735,000, but then plus 3652.5, 3652.5, that's going to give 0.005 psi of t. 0.005 times negative 735,000 is negative 3652.5. The 3652.5s are going to cancel. And these two things are the same if I assume psi of t is a solution of this. A solution of that. Its derivative will be 0.005 times itself. That's what I'm saying. I'm assuming psi of t solves this. And I'm saying if I add it to this equilibrium solution, I'll get a solution of the original. And it's the linearity of the derivative operator that guarantees this. The derivative operator, here's the connection, is a linear transformation. But wait a minute, I thought linear transformations like were matrices or something, as we've talked about in lecture B for this class. Hang on, you will see the connection to linear transformations in a few lectures. Continuing to go kind of fast here for some time. Oh. Continuing. We know a general solution of this equation, of this homogeneous equation, associated homogeneous equation, which we can write in either way. Again, this way, with a 0 on the right-hand side, emphasizes that it's what we call homogeneous. But we can also write it this way. Writing it this way helps you realize this is related to what we talked about, maybe lecture 3 or so. Linear differential equation that we can guess solutions involving E. I mean, yes, you can separate variables here to solve for it, but you're looking for a function whose derivative is 0.005 times itself. It's got to be an exponential function with power 0.005t. Right there, there's your general solution of this. You can find it just by knowledge that you should memorize or just be able to reason out every time. Therefore, it turns out a general solution of the original non-homogeneous equation might be the sum of that thing minus the, whatever it was, 700 and something thousand. 730,500, the equilibrium part. When C is 0, this is going to be your equilibrium solution. And you can check this is a general solution. We can solve for C using the initial condition. Set A equal to 2,000 here, the initial deposit. Plug in T equals 0, e to the 0 is 1, so you just get a C. Solve for C. C turns out to be 732,500 here. And the unique solution of the IDP is therefore this. And then we can use this to find the amount on deposit after 10 years. Plug in T equals 10, and you find that the amount your money has grown to is 39,556.08. Note that if the interest were 0%, and 0.5% is not very large, not much bigger than 0%, the amount on deposit wouldn't be much smaller than this if you didn't get any interest. You have your initial deposit, 2,000, plus 10 times 365.25 times 10. This would be the money that comes from your deposits every instant of every day. You know, you're doing, again, $10 every day. This is the number of days in a year times 10 years. You get this. You get a little bit of interest in the big scheme of things. This would be, there'd be a more extreme difference between these two things if your interest rate was higher. You know, of course, like 8%, that would be great. There'd be a huge difference between these two. So the answer seems reasonable. Hang on, more to do. We still haven't said everything there is to say about linear equations. In fact, we're not even going to finish it this lecture. There will be more in lecture 12a, and maybe even 13a. What can you say about first order linear, emphasis on the word linear, ordinary differential equations? Emphasis on the word linear. It's one of the form dy dt, so it's first order, equals a of ty plus b of t, where a of t and b of t are arbitrary functions of t, possibly even nonlinear. Is that really a good idea to call it a linear equation if a of t and b of t are nonlinear? Turns out it's a good idea to do that. And it's related to the linear operator idea, which is related to linear transformations, which we will see here over time, how it's related. Note that this is, in general, a non-autonomous equation. So relating it to what we've been talking about recently, in general, unless a of t and b of t are constant functions, you would not want to make a phase line for this. For the financial flow example we just did, you could make a phase line for that. Because it was autonomous. A of t and b of t were constant functions in that case. There's a phase line. There would be one equilibrium point way down at whatever it was, negative 700,000 something. That turns out to be a source. You can check the right-hand side function if you graph it. Is a straight line with a positive slope. And so the intercept where the equilibrium point is has a positive slope. And the linearization theorem, which you really don't need to use because it's already linear, says it's a source down there. And the solution that we were interested in based on the initial conditions starts way up there where it was up at 2,000 for A and increased over time. So it moved up. So in general it's non-autonomous, but for our example it was autonomous. This linear differential equation is often written, for good reason, in what's called linear operator form. Essentially subtract a of t times y from both sides. Don't subtract the b of t. Subtract the a of t times y from both sides, right down there. We could leave it like this, dy dt minus a of ty, but oftentimes, so we don't have a minus sign in there, we just give it a different name and call it plus g of ty, where g of t is really negative a of t. Either way is okay. But why did I pick g of t? Well, I just had to pick some other letter. I didn't want to pick b of t. I didn't want to pick c of t because that would be weird because c is usually thought of as a constant. D of t, that would be related to, seem to be related to derivatives. E of t, you know, e is, avoid the number e. Okay, yeah, I picked g of t. Actually, our textbook uses g of t in this situation as well. So g of t is negative a of t. Keep the b of t in the right. That's how we often write it. And that's the thing that's going to emphasize the linearity and also help us guess certain solutions, like with equilibrium solutions we will see. Two even corresponding homogeneous equations. This ODE right here, the original, is non-homogeneous. Non or inhomogeneous when b of t is not the zero function. Not identically zero. If b of t were the zero function, as it would be for the associated homogeneous equation, then it would be homogeneous. And that's what this is right here. The associated homogeneous ODE. This is not the same as the original, right? It's a different equation. Different differential equation, different solutions. but it's related in a nice way, we will see. That's the associated homogeneous equation. Oftentimes you can solve this, maybe by guessing, like we did with the financial problem, or maybe by separation of variables. It can be written this way, and this is separable. This one's not, by the way. This is not separable if b of t is non-zero. You can't separate y and t. Here you could, because you could divide both sides by y and quote-unquote multiply both sides by dt. We can solve this by separation of variables. Do that, divide both sides by y, pretend you're multiplying both sides by dt, and you'd write it that way. And you'd integrate it both sides there. The left-hand side, you get a logarithm, right? ln of the absolute value of y. What about the right-hand side? Well, maybe a of t is easy to integrate, maybe it's not. Let's just leave it as an integral, and maybe we can do the integral, maybe we can't. But to solve for y now, you want to exponentiate to get rid of the logarithm, and effectively you can get rid of absolute value signs typically. I'm just going to write it like this: y equals e to the integral of a of t dt. And call it y sub h as well. This is something Blanchard and Devaney in Hall's book does a lot. Y sub h is you might call it a general solution of the corresponding homogeneous equation. Now you don't see a plus c in here anywhere, you don't see a c times e to this thing anywhere. Realize that if you're really finding the general solution, you'd want to take into account the integral here being indefinite and giving you a plus arbitrary constant, and in fact you could bring that constant in front of the e. But I won't bother doing that, okay? Just realize that that could be done and typically is done in general. So this YH solves the associated homogeneous equation. It doesn't solve the original, but if we add YH to any solution of the original, just like with the financial when we added it to the equilibrium solution, negative 700 something thousand, you are going to get a solution of the original. In fact, if this is a general solution of the associated homogeneous equation, when you add it to a particular solution of that equation, you'll get a general solution of that equation. You'll see that said again here. Here we go. If we can only find one particular solution, call it YP, one particular solution, YP. P stands for particular, H stands for homogeneous. The YH being a general solution involves an arbitrary constant. This YP being one particular solution doesn't involve an arbitrary constant, though we will see that the method of undetermined coefficients requires to solve for constants when we guess what YP should be. There's where the guessing is going to come in, actually in a second place. Sometimes you can guess the YH as well. If we can only find one particular solution, we could add it to YH to find a general solution of the original non-homogeneous equation. Non-homogeneous ODE dy dt equals a of t y plus b of t. In general, we find YP by educated guessing. The official name for this is the method of undetermined coefficients. Sounds fancy, but it's really nothing other than educated guessing. So let's look at an example. Let's solve this IDP. dy dt equals 5y plus e to the negative 4t. So in the context of the notation we've been using, your a of t function is constant, the constant function 5, and the b of t function is not a constant function, and in fact it's nonlinear, e to the negative 4t. This would be a non-homogeneous linear equation. First step is to consider the associated homogeneous differential equation, where you essentially get rid of the b of t, you make it 0. dy dt equals 5y, which you can also write in linear operator form. It's dy dt minus 5y equals 0, but we don't need to. That's, hey, there's your typical linear equation that we talked about lecture 3 or so that you can guess the solution to as an exponential. YH is an arbitrary constant times e to the 5t. That's going to be a general solution of this equation. This is not the original equation. It's not the same as this. It's an associated equation, related, corresponding. This is not a solution of the original, but it's going to help us generate solutions of the original. Now let's rewrite the original ODE, this one here, in linear operator form. That's a nicer form to help us figure out what yp should be. I'll explain why here in a second. To go from here to here, subtract a of t, y from both sides, subtract phi, y from both sides. This is a linear operator form where you've got dy dt plus g of t times y equals something, equals b of t. The reason this is nice, another reason this is nice, actually, we talked about one reason it's nice already, is that it helps you guess what yp should be. Because you look at this and you say, hey, I'm looking for a function whose derivative minus 5 times itself equals e to the negative 4t. And if you think about that logically, that should be a function that involves e to the negative 4t for yp. Right? You wouldn't want to guess a cosine or something, or a sine, or a power function like t squared or something. It makes sense to guess some constant times e to the negative 4t. Guess that yp equals, call it a times e to the negative 4t. Now, a is not an arbitrary constant. It's a particular constant. We need to solve for this particular constant. How? By substitution. First, into the left-hand side of the differential equation in the linear operator form right here. So find its derivative and subtract 5 times itself. The derivative of this by the chain rule would be negative 4a e to the negative 4t, which is what you see right there. Minus 5 times the function. Here's the 5 and here's the function. Simplify this. These are like terms, so to speak. You're going to get negative 9a e to the negative 4t. I want to set that equal to the right-hand side function, e to the negative 4t. This thing needs to match that thing. And I want these to be equal no matter what t is. Left-hand side has to equal right-hand side for all t. The only way that's going to happen is if negative 9a is the same as the coefficient of this, 1. Negative 9a must be 1. Therefore, a is negative 1/9. C is arbitrary, a is something particular. So a general solution of the original ODE, is now a sum yh plus yp, where yh is really a general solution of the associated homogeneous equation, and yp is this thing, one particular function that solves the non-homogeneous equation. Okay? Are there other particular functions? Yeah, there are, but this is certainly the simplest form of it. This is another place where we're going to see a connection to linear algebra in lecture 11b. This writing a sum of a homogeneous solution plus a particular solution that's going to come up in the context of systems of linear equations in lecture 11b. Now solve the IDP. Plug in t equals 0 and y equals 3. Your initial condition is right here. I'm plugging it into here. Replace y with 3, replace t with 0, get c minus 1/9. Add 1/9 to both sides. 3 is 27/9. Plus 1/9 is going to be 28/9. Plug that in there and you get your final answer for the unique solution of the initial value problem, this thing right here. Okay? This is the final lecture for slide for lecture A. Let me just remark, and we'll look at this more in lecture 12A, that if your differential equation to begin with, you'll say the same thing as this one right there, but maybe with a trig function on the right-hand side, like cosine 2t or something, and you think about trying to find a particular solution of this, maybe by subtracting 5y from both sides first, you should not just guess a cosine function. You should also include a sine function in there. You'd have some constant times cos 2t plus some constant times sine 2t. You get 2 unknown constants that need to be solved for. And that could lead to a system of linear equations and be another relationship to linear algebra. Is this the end? Yes. Okay, thanks for watching lecture 8. please watch lecture B2.